All right, let's get started, everyone. I am Rajiv Balasubramanian from the University of Utah. It is my great pleasure to introduce the speaker for the second keynote of ISCA 2024. Shridar Iyengar is a vice president of research at Intel Labs. He's the director of Intel security and privacy efforts. He received his bachelor's degree in electrical engineering from IIT Madras and his master's degree in computer science from the University of Wisconsin-Madison. His areas of research include secure architectures and innovations to protect confidentiality, integrity, privacy, and identity. Over the years, he has sent several team members of his to ISCA, but this is his first time attending ISCA. He's here to tell us about an industry perspective on an enduring trust architecture. Shridar, it's all yours.
Thank you. Well, good morning, everyone. And thank you, Rajiv, for that nice and brief introduction. Thanks also to Sandhya for inviting me to ISCA this year. As Rajiv said, this is my first ISCA ever, and I feel quite privileged to be here, making history together, as Augusto said yesterday, in this wonderful city of Buenos Aires. And it's my privilege to be sharing some perspectives on trust architecture. Before I begin, a brief overview of Intel Labs, for those of you who are not familiar. We're one of the two big research arms of Intel. There's component research that deals with process technology and Moore's Law. Intel Labs is a research organization for the business units of Intel, and we've got all kinds of areas of research, all the way from circuits to microarchitecture, systems, IP design, all the way up to the top to AI and more AI. And security, of course, cuts across the stack here. So I feel, again, greatly privileged to be here. And it was very heartening in the last couple of days to see many people that have been collaborating with Intel Labs and interned at Intel Labs and gone on to bigger and better careers in the academia. So with that, let me get started. I'd like to start with a rather simple observation that should not be a surprise to anyone in this room. And that is, we see attacks are increasing. They're increasing in volume, they're increasing in sophistication, and in impact. To your left is data from NIST's National Vulnerability Database going back 20 years, and they see an increase of 12x over that period. In the middle is an increase in zero-day in-the-wild attacks. Now, these are attacks where the adversary has exploited a bug in the software well before the developer has a chance to fix it, hence the term zero-day. And it shows a degree of sophistication on the behalf of the adversary. And then lastly, not a day goes by when we don't hear of some data breach or the other, some ransomware or the other, where the victim is forced to pay up. And the aggregate cost to society is in the millions, if not the billions. Now, it's one thing to lose your data, but attacks on cyber-physical infrastructure implies potential loss of property and, of course, potential loss of life. And then there's AI. Not too long ago, some prominent folks in AI issued an open letter talking about the risk of extinction from AI. Now, whether you believe in that or not, the threats from AI are quite real, all the way from amplified misinformation to biases in our model to weaponized deepfakes. So just to cut a long story short, increase in attacks on these three vectors are a global problem and an industry-wide problem. So the natural question to ask is why? Why is security so hard to get right? Well, to begin with, we live in an ever-increasing digital data economy, right? We are generating data, we are consuming data by the petabytes, if not zettabytes. And all this is, of course, good for us as a society. We got a lot of good insights from data that's helped us create new products, new consumer experiences, remove inefficiencies from an organization, and so forth. So data is monetizable, data is valuable, and therefore target of a lot of attacks. In security, we have a saying, threat follows value. To make matters worse, we also have an ever-increasing threat surface. Just to take an example, in the middle, the Linux kernel lines of code is well north of 25 million lines. Now, it's very hard, if not impossible, to write millions of lines of code without bugs. And if there are bugs, they're exploited, and all the adversary has to do exploit one bug, find his way in, and the game is over. On the defense side, however, we have to protect all the possible paths into the platform. So the deck is stacked against the defense. And lastly, we have the industrialization of hacking. Right? The adversary is extremely well-resourced, extremely well-motivated, all the way from fame and notoriety to economic gains to even cyber warfare. They, of course, use all sorts of modern software development techniques, shared libraries, DLLs, SDKs, machine learning. Even ransomware is available as a service. So the bar to get into this area is rather low. Because all this is not lost on the ecosystem, certainly not lost on Intel. For the better part of 2 decades, we've been focusing on security. It's been a key priority within the company, and we've generated many, many technologies. It's a bit of an eye chart here. So what I'm going to do is just talk about the 3 yellow boxes. On the top, we have mitigation against what's called a ROP attack, or return-oriented programming attack. What the adversary does in this case is rather than inject malicious code into your platform, what they do is they scan your code, look for snippets of instructions that end in a return instruction, they're called gadgets, and stitch it together to create a Turing-complete program. Except, in this case, it's a malicious Turing-complete program. So essentially, they turn your own legitimate code against you. So we came up with control flow enforcement technologies, and with the help of the ecosystem, ROP attacks are on the decline. In the middle, we have SGX. We've known for a long time that applications need a safe place to stand, a safe place to execute the code and data. So SGX is a trusted execution environment where the hardware provides certain security guarantees of confidentiality and integrity. It's available in our platform since 2020 in our servers and widely deployed by cloud service providers. And lastly, we have AES, and none more foundational than AES because it's the foundation for a lot of data encryption on our platforms, available since 2009 in billions of platforms. So all this is well and good, but this is looking backwards. The real question is, what does the next decade look like? What does the adversary in the next decade look like, and what should we do to build enduring, trustworthy solutions that stand the test of time? So for this, we need to take a lot more proactive approach to trust. And I'm going to cover 3 different areas of security. One, of course, is AI. AI is pervasive, and so it's incumbent on us to start defending the AI pipeline, the AI assets with today's well-known defenses. The second is quantum resilience. We need to start being aware of a future adversary and start building in defenses proactively, well ahead of the onset of quantum computers or quantum attacks. And the third is data privacy. I talked about being in a data economy, a digital data economy. So it's also incumbent on us to raise the bar on data privacy by looking at things like enabling compute on data without ever exposing it. So let's start with number 1. We've all witnessed unprecedented growth in AI, right? Including the size of AI models. Back in 2018, BERT, released from Google, was about 240 million parameters. And 5 years later, GPT-4 came with 1.8 trillion parameters, right? That's a growth of 10x every 18 months. With the growth of size comes a commensurate growth of cost of these models. And that's what this graph is all about. It essentially shows the cost of compute equipment for one training run of a model, just the cost of the compute equipment. And taken over the past 13 years, the data is gathered since 2009, it shows half an order of magnitude increase year over year. So clearly, these AI models are very, very expensive to train and getting more and more expensive. Along with that, we've also seen a commensurate increase in attacks. The most obvious is stealing the model, right? Anthropic and OpenAI are very concerned about model stealing because it's a lot easier to steal the model than build one. But we've also seen many AI-specific attacks, like adversarial attacks or adversarial training, where a small perturbation in the input image causes the AI to misclassify. There's deepfakes, there's loss of data privacy because of model inversion attacks or model inference attacks, attacks on LLMs, and so on and so forth. So if there ever was a case to be made for threat follows value, this is it. Now, at the same time, we've also seen a rise in an area called confidential computing, which protects the data in use. Basically, this is an area where we protect the data and code as it's running, as it's being computed on, through a mechanism called trusted execution environment, where the hardware provides certain security properties. Property of confidentiality or secrecy, property of integrity or ensuring that the data is tamper resistant, and the third is remote attestation. This is where the hardware provides encrypted evidence of the state of the execution environment, so the third party is comfortable enough and can release their secrets into the TEE. Now, many companies have technologies in space. Intel has SGX, and that's the picture in here that protects the applications inside the white box. Another one called TDX protects the whole virtual machine, the white box including the operating system and the hypervisor. And there are similar technologies from AMD and ARM. So the natural question is, can confidential computing be used to protect the AI assets? And the answer is yes. And as it turns out, confidential computing is one of the more frequent use of confidential AI is one of the frequent use of confidential computing. Now, there are many players in the AI pipeline, so to speak. There's the AI model creator, so to speak, and they've just spent a lot of money creating it. So when they deploy it for inference, they want to make sure it can't be stolen, nor can be tampered with. If you're the end user, you want to make sure you get the exact model that you asked for, and you want to protect your data as you send it forth for inferencing. And if you're the cloud or the edge provider, you want to make sure that the process or the service provided for inferencing or training is protected as well. So the requirements of all these three are met by a trusted execution environment. So in this case, you load up your model and data inside, in this particular case, SGX. The memory is encrypted, the bus is encrypted, and is decrypted only as the data is brought into the CPU package. So this is how the model or the data inside can be protected from being stolen. I want to give you a couple of examples here of how this is used. How does one protect large language models? Now, we all know these very large giant models like GPT-4, but at the same time, we've seen the emergence of much smaller, targeted retrieval-based models. We call this nimble models, or nimble generative AI. Now, the cutoff seems to be around 15 billion parameters, and largely driven by, it's an empirical data, empirical observation, largely driven by the growth in these open source models, which are in the 13 billion to 15 billion range. Now, to be sure, the giant models aren't going to go away. In most likely, they'll grow larger by absorbing the world's data in pursuit of artificial general intelligence. But the nimble models are almost as good in targeted tasks as these giant models. And they have this additional advantage of being cost-effective, easier to develop, easier to deploy, easier to integrate into applications, and of course, a wider choice of platforms to deploy with. Now, if I have corporate IP that needs to get trained on, if I have privacy-sensitive data to be trained on, what I don't want to have happen is be that part of some foundational model's parametric memory. I don't want some foundational model to memorize a company's private data. So the other option to do this is through a mechanism called RAGs. You augment the generation model with a retrieval model. And essentially, your corporate data is kept in a curated database. The query comes in that's vectored into the RAG database, which that model retrieves an appropriate document. It's fed back into the Nimble model, and then off you go. So the obvious advantage here is it gives rise to a lot of domain-specific models. And because of the fact that the corporate IP or privacy-sensitive IP is not remembered in the model's parametric memory, it's sort of secure by design. And you can augment that with SGX, in this case, by further protecting the RAG model and the language model as well. The natural question then is, well, how expensive is this? So one of our customers did an independent evaluation, and they found that a Nimble model, Llama 2 in this specific case, cost about 3% overhead in running in a TE. So at that, it's pretty reasonable, and there's no reason not to do this all the time. Another example is federated learning. It turns out that one of the most challenging problems of developing a model is access to data. And for a variety of reasons, people are either unwilling or unable to send the data to a central place where you do the training. And we call this problem a data silo problem. Because of regulations or data sovereignty rules, data exists in silos because of maybe unwillingness to send because of corporate IP reasons or what have you. So rather than send data to compute, which is what happens in a traditional training model, we need to change the paradigm here, send compute over to data. And that's the federated model. So in the case of these endpoints, they have their own local data. And the way it works is it initially gets an initial model that's trained locally in each of the sites. And only the delta, the change in the model, is sent back to an aggregation server, which builds a new model, aggregates it, sends it back again, and you go through the loop again. So this way of learning, federated learning, we partnered with University of Pennsylvania's Perelman School of Medicine to deploy the world's largest healthcare federation, along with 71-odd medical institutions in 6 different continents. The problem they wanted to go solve is called brain tumor segmentation. Essentially, they wanted to define the contours of the green region in an MRI scan. Now, a lot of these medical institutions have MRI data, but none of them have enough to generate a good model. So they have to pool the data, except they're not going to send the data to a central place. So federation is the only way to go, or one of the more, or at least we posited that. But there was a lot of skepticism from the hospital IT, whether this will work or not. But when they actually saw that the data never leaves the platform, and you could augment the security with things like SGX and provide model confidentiality, and the integrity assumes that everyone plays by the rules, only approved models are being used, and so on and so forth, they grew a lot more confidence. And over the years of a couple of years, we were able to improve the accuracy of the model by 33%, which is significant in the medical community. And all this can be found in a Nature paper that we published in 2022. Now, by now it's pretty clear, I'm a huge fan of TEs, I'm a huge fan of SGX, in large part because the original research from SGX came from my lab about 15 years ago. But I'll be the first to admit that this is not a panacea. There are many cases, there are many attacks in AI for which you need novel AI software techniques to protect against AI attacks. So I'm going to go through cases that show AI versus AI. One example is called adversarial attacks. Now, back in 2014, a researcher named Szegedy figured out some intriguing properties of neural networks. And he wrote a paper by the same title, Intriguing Properties of Neural Networks. What he observed was that certain well-formed small perturbations in an input image can cause the AI model to massively misclassify. And since then, there's been a lot of research in this space. Our interest is in applying this to adversarial objects, to real objects. So what we've done is created an adversarial image on a T-shirt as is shown in the image on the left-hand side. And the vision model misclassifies him as a bird rather than a person. Similarly, we can create adversarial graffiti where the person standing in front of it is basically invisible. And by that, I mean the machine learning classifies the person, in this case, as a teddy bear, not a person. Now, imagine walking down the street, or more crossing the street with one of these T-shirts, and your vision model in an automated car thinks you're a bird, right? Nothing good can come out of that. So DARPA was quite concerned about this, and they created a program called GUARD, enhancing system resilience against a wide range of adversarial attacks. And we were one of the performers, along with Georgia Tech, and we created many solutions. We were trying to figure out if JPEG compression, for example, can eliminate high-frequency components and therefore remove the adversarial patches, or use adversarial training, which is actually quite popular, except it's very expensive. So what we did was pursue a solution that's based on generative AI. It's called generative resampling defense. And the way this works is generative models are trained on a lot of natural-looking images. And they know the probability of a lot of these natural-looking images in your training data. And Gen AI, like Stable Diffusion, that you might have seen before, essentially takes a text and generates an image, right? You can say, create me an image of an ISCA researcher wearing a T-shirt, riding the Iguazu Falls, and out pops an image, right? What we did was to use Stable Diffusion in a different way. We use it to resample an image. And here's the way that would work. What we do is we take this adversarial graffiti, you throw in some Gaussian noise at it, and ask it to resample the same image. Now, because it's trained on natural-looking data, as it denoises the image, the adversarial patches and the adversarial components of the image are naturally, by design, left behind. So this has been pretty effective, as it's shown over here. The person is correctly identified as a person on the same adversarial image. And we submitted this to DARPA, and they concluded that it's fairly effective at stopping hallucinations. I can't talk about AI without talking about deepfakes. You all know what it is. The internet is full of deepfake videos. It's essentially created using deep learning technologies, and it's put to a lot of malicious uses. And these deepfakes have become quite realistic over the years, and many of the countermeasures rely on the fact that the deepfake generation leaves behind some artifacts that might be too subtle for the human, but can be detected through forensics or machine learning techniques. So just to give you some examples here, when you blend in generated content onto a frame, it leaves behind some spatial artifacts that can be detected either through edge detection or some sort of frequency analysis. When you do the blending, sometimes it's incongruous with the environment, and for example, the lighting might not be quite the same. And of course, there's forensics left behind by GANs that can be used as well. Similarly, there are temporal artifacts left behind, either through physiological differences, or perhaps the more popular one is lack of synchronization between the mouth structure, which is called visine, or spoken utterances, which is called phonemes. Our approach is on the physiological space, and we look at a lot of biological signals to differentiate between a deep fake and a real video. We look at a property that's uniquely human, and that's blood flow. It turns out that blood flow creates some subtle changes in skin color. And we use this technology called photoplethysmography, or PPG, to detect this. That's a long word, but you all are actually familiar with it. If you ever go to the doctor's office and they put the sleeve in your finger to detect pulse oximetry or blood oxygen level, that's based on PPG. So essentially, it's a technology that's it's a sort of an optical technique to detect changes in volumetric changes in blood flow in the organs. So we measure PPG values in the spatial domain, in the temporal domain, and spectral domain, and eventually to differentiate fakes from real videos. And the results sort of speak for themselves. Now, the natural question is, can the adversary mimic PPG information? I think our assumption right now is not, because PPG is not differentiable, but I wouldn't put it past a future adversary to do so. So we have to develop defense in depth in this case, and we're looking at other physiological signals like gaze tracking, eye tracking, tracking voice as the head moves, and so on and so forth. Eventually, we have to assume a sort of belt and suspender model to create a suite of biological signals to detect deepfakes. Now, I've gone through a few mitigations of AI, but we're a long way from saying in AI we trust. Okay? And here's a list of the things that I think are still challenging. We need to scale confidential AI to heterogeneous platforms. And there was an article from OpenAI a few months ago asking for trusted computing to be deployed in all platforms where AI is being used, specifically GPU and accelerators as well. The second point here is we need the availability of a high assurance AI supply chain. We need to think of this as a supply chain problem to deal with both the data sourcing and the model as well. So we need to know the provenance of the data, the authenticity of the model before we start using them. We always need metrics. Of course, metrics need to create robust AI models, but beyond that, we need metrics to resolve conflicts between things like privacy and fairness, between privacy and utility. Most of the deepfake work is on deepfake faces. But what about deepfake satellite images or satellite video? So we need generalized deepfake to span different domains, different generators, and different modalities. And in order to secure something, you need to know what you're securing. So a high degree of transparency, and we need to build AI models assuming it'll get broken to be resilient to these kinds of AI attacks. And lastly, we're moving to a world where it's no longer one model, where people are using multiple models to create solutions. The RAG thing I talked about earlier uses two models, a retriever model and the whole LLM. And there are things like Lava, for example, uses a language model and a vision model. So we're rapidly moving to a world where multiple AI models are being used. And so the implications of trust is still an open problem. Okay, now for something completely different. Quantum computers. Now, quantum computers offer great promise. The promise of solving these very hard, intractable problems that can't be done through conventional computing. And even though they might be quite some years away, maybe even decades away, they have the promise of solving these hard sciences like protein folding, drug research, or material design, and so on and so forth. Now, many companies are working on quantum computers, and so is Intel. And our approach is in using our expertise in high-volume transistor manufacturing to create and control what are called hot silicon spin qubits. Now, I'm not a quantum physicist, so that's all I'll say about this topic. However, what I'm interested in is the impact of quantum computing on classical cryptography. Now, for those of you who are not quite familiar, allow me to give you a 30-second primer on this. On the left is symmetric cryptography, and this is the case where the same key is used to encrypt and decrypt a message. And I talked about AES earlier. That's an example of symmetric cryptography. Public key cryptography, on the other hand, uses two keys, a public key and a private key. And the private key is kept private, and, well, the public key is kept public. But the more important fact is these two keys are mathematically and uniquely linked. And the use case for this is message authentication. So in this case, Alice would sign a message using her private key, and anybody out there can verify the signature using Alice's public key. This way of authenticating messages is sort of the foundation of trusted communication over the internet and utilized by RSA and ECC. Now, back in the mid-90s, a couple of researchers from AT&T figured out something quite interesting. Grover came out with an algorithm that speeds up unordered search. Okay? Normally, we all know unordered search takes about an order of n. Using Grover's algorithm, you could speed it up to order of square root of n. So just to give you some numbers as an example, if you apply unordered search to search for an AES key, it would take you 2 to the 128 tries if you do a brute force search. But using Grover's algorithm, that gets weakened to 2 to the 64. Still a large number, but a far cry from 2 to the 128. So we say Grover's algorithm weakens symmetric cryptography. But Shor's algorithm figured out something even more interesting. He solved integer factorization and discrete log problem. Just to put it in layman's terms, what he figured out is a way to take a very, very large number and break it down to its constituent primes in polynomial time. He figured out a way to do this in order of log n time. So taking the same example as earlier, what would take 2 to the 128 would take 2 to the 7 tries. That implies public key cryptography is broken. So this, of course, has a lot of people worried because the consequences of these attacks are pretty dire. I said AES is weakened, which means eventually the confidentiality of private data will be broken. If you can't distinguish between a good message and a bad message because of Shor's algorithm, you can't distinguish between a good software update and a malicious software update. And that goes for firmware updates, and that goes for microcode updates as well. And for the same reason, a lot of the transaction over the web will be compromised as well. And so I said, this has gotten a lot of people worried. The White House issued an executive order back in January of 22, asking for people to pay attention to this. The NSA issued an advisory recommending the adoption of both quantum algorithms created by NIST and IETF. But more importantly, they set forth a timeline for all DoD, Department of Defense, national security systems to follow. And the first yellow line, it's hard to read, but talks about software and firmware update. They want DoD systems to start transitioning to post-quantum crypto starting 2025 and ending in 2030. The same goes for network equipment. That's the red line there. And OS and other applications have a little bit more time. But they expect this transition done by 2033. Now, that's not that far away. The reason we should be all concerned is because we know of adversaries that are harvesting encrypted data. You talk to any chief security information officer out there of a Fortune 500 company, and they'll talk about adversaries copying or harvesting encrypted data today in the hope that one day when you do have quantum computers, they can go back, break today's crypto, and get access to long-lived secrets. So they'd like to have a solution now. The second problem is crypto transition takes a long time. The development of new crypto algorithms and deployment and adoption takes a long time. ECC, elliptic curve cryptography, for example, was discovered, we've known since 1980s, but it took full 20 years to adopt it. More recently, SHA-3, for example, was standardized in 2015, and it's still not widely adopted. So the companies are very, very conservative when it comes to adoption of new crypto algorithms. Third, we've got long-lived platforms. You know, the life of a server is somewhere near 15 years, 10, 15 years. But the lifespan of IoT devices can be 2 or 3 decades. That's well in the era of quantum computers. So if you release one of these things now, you'd want to have them protected against quantum attacks. And lastly, there's a lot of excitement and heating up of standardization. To give you a little background of what it takes to get one of these things done, NIST issued a call for proposal back in 2016 for asymmetric algorithms that specifically focused on what's called key encryption or digital signatures. And they got about 70-odd proposals. And fast forward 8 years, we now, by the end of this year, they are likely to publish the 4 winners. And they were taken from a variety of different mathematical families because they wanted diversity of algorithms. Hash-based systems was one algorithm, and largely because the security properties of hash functions are pretty well known. Another one was lattice-based crypto. For those who are not familiar, this came up in 2005 by a researcher named Regev, and he figured out by introduction of a small amount of noise in a system of linear equations makes it an extremely hard problem to solve. And this is used as a hardness assumption for many new public key cryptography algorithms. And there are other families as well, but they're largely irrelevant because the winners, or the spec that's published now, are largely based on lattice-based and hash-based. And the reason is lattice-based solutions are the security properties are well understood, and they can be implemented quite easily. But the key sizes are pretty large, so there's no free lunch here. So what does it take to build quantum resilience? So this is our approach. We think of it as 3 separate parts. The first is to develop resilience against this whole data harvesting problem. And I said earlier that AES is weakened, right? An easy way to strengthen it back is to double the key size. So we have our platforms deployed with AES-256 and a similar increase in the SHA digest as well. The second part is protection against this malicious software update. So we do a lot of microcode updates, and it's of grave concern for us that not be compromised by quantum computers. So a lot of our code signing infrastructure is updated to issue quantum signatures, and our platforms, in fact, starting late last year, can now verify a quantum signature. And we use a hybrid mechanism here, both classical and public key cryptography. And the last is, of course, the post-quantum standards I talked about. We've participated in this since the last 8 years. We've submitted proposals, we've implemented them, and optimized them for our platforms. But there are still a lot of implications or hurdles for adoption. And here's some data that talks about the key sizes that's more specifically. As you can see, they're in the range of 1,000 bytes, somewhere in 1,500 to 7,000 bytes. Now that's about 10x, or even 100x compared to conventional cryptography we enjoy today. So there's still a lot of issues in implementing this efficiently. There's impact on how long it takes to compute them, transfer them, store them, and so on and so forth. Now, we need to deal with a lot of heterogeneous mathematical families as well. And so how do you deal with that? Is there commonality in terms of mathematical properties? Can we do some hardware-software code design so you have one interface that deals with these diversity of mathematical families? So there's some challenges here. But perhaps the most major challenge is crypto agility. I talked about NIST announcing final candidates this year, but they're not going to be satisfied there. There are some new proposals coming that are based on code signing, the new signature proposals. So still a lot of innovation in here for academic community that want to participate in these new post-quantum algorithms. Now, we all talk about hardware, but the real challenge is the software side, because migration of software that uses post-quantum, like TLS, direct anonymous attestation, VPNs, and so on and so forth. That's sort of the major challenge to do the migration. And there's a lot of work in securing the cryptanalysis for this, for those academics that want to deal with it. Side channel mitigations, fault injection, developing formal verifications for these things is a huge challenge that needs to be done as well. Okay, data privacy. So in 2010, a researcher named Craig Gentry proposed the following question. Is it possible to delegate processing of your data without giving away access to it? Now, this feels like a bit of a fallacy. Now, how do you let the cloud process your data, compute on your data, without seeing your data or getting access to it, right? So it feels like an impossible statement. But it turns out that this is a false dilemma, because in the end, you can have your cake and eat it too, through a mechanism called fully homomorphic encryption. What this is simply put, computation directly on encrypted data. Okay, so the way we see this work is a user would encrypt the data using his or her public key. The encrypted data would be sent to the cloud. The cloud would perform operations directly on the encrypted data, generating further encrypted data, which then be decrypted using the user's private key. The thing to remember is data stays encrypted at all times, during transit, during storage, and even during compute. So it's no wonder that DARPA calls this the holy grail of cryptography. Now this sounds too good to be true, doesn't it? So where's the catch? It turns out that when you encrypt something homomorphically, the ciphertext, in this case, for an integer, is two very large polynomials with very large coefficients and a very large degree. So when you run the numbers, a 4-byte integer results in more than 1.7 megabytes of data. So it's a huge data explosion. To make matters worse, there's also a compute explosion problem. When you multiply two numbers in clear text, and if you want to do that in ciphertext, you're basically multiplying two very large tuples of polynomials. So we're talking about thousands and thousands of polynomial modular arithmetic, thousands and thousands of modular arithmetic operations. So in the end, what happens is one CPU operation results in millions of equivalent operations in the ciphertext domain. So the natural question is, where are we with current hardware? So in this graph, the y-axis is the overhead of FHE, and it's in log scale. So the higher it is, the worse the number. And if you normalize it with CPU, which clear text, which is 1 in this case, the first graph shows the overhead if you do homomorphic operations in the CPU today. And that's about 6 orders of magnitude, 1 million times slower, because of all the reasons I talked about earlier. If you do this on a CPU with AVX'512 and multi-core and all the good stuff, you get about a 40x improvement. If you do this with GPUs and all the SIMD advantages you have, you get about 140x improvement. But that's a far cry from where DARPA wants to go. What DARPA wants to do is create 100,000 times performance improvement compared to the first graph on the CPU side. They want to create 5 orders of magnitude improvement, right? And they started a program called DEPRIVE, Data Protection Virtual Environment, and Intel is one of the performers. So this is truly a grand challenge. And for this, you need a new architecture. On the left-hand side, the reason you need it is you have to deal with the operation complexity of polynomial modular arithmetic. So the basic element of FHE is this butterfly operation, as I show in the left-hand side figure, which involves 2 multiply-add operations. And again, if you optimize this in today's CPU with AVX'512, that takes about 4,800 cycles. What we need to do to get to DARPA's guidelines is to bring it down to 1 to 2 cycle throughput. We need to get 3 orders of magnitude improvement. In the middle are the implications of the data explosion thing I talked about. Now, each polynomial has 16,000 coefficient, and each coefficient is 512 bits. So if you do the math, that's what gets you to 1.7 megabytes. Now, these coefficients are involved in a lot of these different operations. So while there's inherent parallelism in the data, you need lots and lots of compute parallelism as well, way more than what the CPU offers today. You need of the order of 8K to 16K way parallelism. And the last is something very uniquely FHE. A large number of FHE operations deal with this thing called number theoretic transform. NTT is essentially a very efficient way of doing polynomial modular arithmetic. You can do this in the order of n log n. And one of the things you need to do for NTT is you need to align all the coefficients so you can do the operations simply. And if you use the today's permutation engines that's available in CPU and GPU, that takes up the order of 100 cycle latency. Again, we need 2 orders of magnitude improvement to less than 5 cycles. So as you can see, this level of performance expectations can't be done in today's CPU. If you look at GPUs, clearly they have lots of parallelism, but it still doesn't do the other two things. So you truly need a new architecture. And this is what we set out to build as part of the DARPA program. It's a research hardware accelerator for FHE. And the compute engine has lots and lots of functional units that are optimized specifically to do the NTT operation I described earlier. To deal with the data explosion problem, we use high bandwidth memory. And we also need to deal with data flow design for just concurrent transfers of data through the memory hierarchy, from HBM to the on-die memory onto the compute engine. You cannot let the compute engine stall. And then, as Matteo described yesterday, there's a lot of hardware-software code design needed because there are multiple schemes involved in FHE. I didn't talk about them necessarily, but there's BGV, there's BFV, there's CKKS, there's THFE. So lots of different schemes that need to be dealt with as well. And so, and that requires a hardware-software code design. Another thing the hardware does, the architecture does, it treats polynomial as a native data type. And it exposes an ISA that directly operates on polynomials. So you can do addition, multiplication, whatever, directly on polynomials as well. And you need a compiler framework that can take a Python program and translate it to this sort of polynomial ISA architecture. And there's innovations in the compiler themselves. It's like no other compiler we've known. It's got a lot of intermediate languages, very similar to MLIR, but also has to deal with things like noise management, with cryptography, as well as translation into these unconventional architectures. And also, just to speed up development, we're using existing libraries from Microsoft and OpenFHE. But DARPA is just interested in 5 orders of magnitude. And what we wanted to go well beyond DARPA. So we've started an academic center with a lot of academics involved in not just FHE, but they're working on post-quantum crypto, lightweight crypto, as well as FHE. And we want to answer questions like, what is the additional tool chains involved? We need to do a lot more cryptanalysis. And this is architecture truly scalable for all the kinds of things we imagine we can do. To make something enduring, at least in the industry, you have to deal with standards. And when none exist, you have to pay the price of creating one. So here we've engaged with ISO and IEC to start a standard specifically to deal with FHE, the different schemes, the different parameters, the use cases, and so on and so forth. And we have a lot of support from a lot of different countries here, and we expect a standard to be available by the end of this year. Okay, while there's a lot of promise, we still have a long ways to go. On the architecture side, we know how to build very fast compute engines, but we're still limited by the bandwidth I/O to the chip. So the memory bandwidth is still a big challenge here. So eventually, I think we'll need some very fast, very dense memory where we can store these FHE keys and FHE metadata closer to the chip. So things like 3D stacking, ferroelectric memory, and things like that. There's still a lot of work done on the crypto optimization. One of the unique things about FHE is there's always a trade-off between noise management and performance. I didn't go into much detail here, but if you do a lot of operations, a lot of optimizations, the noise automatically rises as well, dramatically rises. And if it goes beyond a certain threshold, you can't get back the clear text. So you need to constantly manage the noise as you go along. And there's some details and things like relinearization of the polynomials, bootstrapping, and things like that, which in turn has a performance cost as well. So there's a lot of work still to be done in sort of noise management trade-off versus performance. If you really want to scale use cases, the hard problem eventually will not be hardware, it'll be software. And how do you enable these applications with tools that can automatically translate into this FHE paradigm? FHE naturally involves data oblivious programming. Remember, everything's encrypted. Even an if-then-else condition is encrypted. So how do you do if then else? How do you loop conditions when the condition itself is encrypted? Now, there are techniques for that, but doing it automatically, impervious, where the user remains impervious to that, that's the challenge here. And of course, we talked about mature standards as well. Now, all the issues notwithstanding, and I truly believe that if we do this right, we will usher in an era of encrypted computing. We'll be able to do things that we can't imagine. Things like doing machine learning without revealing the data or the model. Right? If the model is public, then the data can be encrypted, including things like encrypting your query as part of the LLM. Second is determining these overlapping data sets without disclosure. It's also known as private set intercept. Essentially, this is Microsoft, for example, uses this for user password detection. Essentially, what they do is they encrypt homomorphically all the user passwords and encrypt the passwords they get from the deep web. And if there's an overlap, then your password is leaked. So they're able to do this without looking at your password in plain text. There are all kinds of other use cases where I see this coming, especially in terms of operating in the medical domain using DNA and things like that. Search without revealing intent is another use case. Imagine typing in a phrase in a browser, right? And the browser vendor doesn't know what you're looking for. You've seen cases and heard stories about the browser vendor knows more about you because they know of all the search terms, and you have these weird ads appearing because of this. And lastly, outsourcing compute without revealing data. That's the original use case that Gentry started with. So in closing, I've been doing this for north of 18 years. These are the lessons that I take away in sort of dealing with trust in a more proactive manner. One is we need to be extremely agile when we deal with AI and crypto. We deal with security aspects of AI and crypto for different reasons. AI is extremely fast-moving, right? And the mitigations and attacks happen almost fairly frequently. So we need to be extremely agile for that reasons. Crypto is different. Crypto moves extremely slowly. But by the time the attack happens, it's too late to think of agility. The agility you need to think of when you design the crypto systems. So this whole cat and mouse game is very, very central to AI and crypto. Second is, wherever possible, we should build defenses proactively. Now that sounds obvious, but in the security world, oftentimes we are building defenses well after the attacks happen. We see a lot of attacks happen, a lot of systems are sacrificed, and then you build a defense, and then it's deployed. By that time, it's almost too late. So wherever possible, we ought to start doing this in a proactive manner. This phrase here, security is value expected, privacy is value added. I owe that to Todd Austin. In our research with Todd Austin, he said this, which really resonated with me. As we talk to customers, they expect our platforms to be secure against these attacks. However, when we talk of privacy, they're a lot more open to adopting privacy-related thing or adding, monetizing privacy-related technologies. So we really need to raise the bar on data privacy. And the last thing is, it's a bit of a sobering note in some extent, but in security, there's no panacea. There is no one remedy in security. And we need to adopt a more defense in depth posture. We need to have a sort of belt and suspenders approach when we deal with security technologies. Okay? With that, I'll end. Thank you very much, and I'm open to questions.
We have time for a few questions, so please approach the mic, state your name, affiliation, and go for it.
Hi, Shridar. Thank you for the presentation. Very, very nice. Tamara Lehman from University of Colorado Boulder. I'm curious, so you mentioned briefly about metrics, right? And you mentioned fairness and privacy, but do you have any thoughts on how to build metrics for security so that we can actually do defense in depth, like you said, and actually have a way of measuring the trade-off between performance, security, and all this, these things.
It's a hard problem, and I don't believe metrics exist properly. They exist for things like cryptography, where there's a mathematical foundation, right? But for things like confidentiality, integrity, there exist metrics. But they're really not much for AI robustness. It's truly an open-ended problem. So I really need help here in terms of getting the academic community, maybe either modeling it or figuring out ways to come up with some, perhaps even heuristics would help, if not metrics.
Thank you.
Paul Farabowski, HP. Actually, my group works on trustworthy AI, and many of the reactions we get from folks outside of a regulated industry is if it costs me something, or if, more importantly, if it slows down the AI adoption, I'm not interested, I'm going to manage risk in a different way. So how do we fix that?
This is the common challenge of all security solutions. And the first time we go to meet a customer, that's exactly the response we get. Just about in every security endeavor, the initial proposals are often more expensive, and with time, the cost decreases. And that's true of AI too, because a lot of dollars for AI is focused on performance, right? Not on security. But security is sure to follow. There are going to be so the more we depend on AI, the more value, the more it becomes valuable to us. All it takes is one attack, and all of a sudden it's the most important thing, right? So we often in security, when we go to customers, there's always like, we don't care, you're late, right? So I think it takes time for this. Unfortunately, what we typically do is go to people that really care about the data. That's why the federated AI, we went to the medical institutions rather than other people, right? Rather than a cloud service provider, we went to the hospitals, and they really had a problem. That brain tumor segmentation was a genuine problem to solve, and they were willing to take the hit to do the overhead to do it. So a lot depends on the use case, and if you get the right partner, the right use case, that gets the ball rolling, and eventually the cost will come down. The cost of the mitigations will come down. That's our approach. That's the approach we've been taking for many years.
So just a quick follow-up. Do you see regulation like what the EU is doing with the AI Act playing a role in this?
Absolutely.
A good role or a bad
absolutely. Role? Eventually, I absolutely think there'll be regulations on AI. It's already happening, the EU Act you talked about. There are a lot of privacy laws, GDPR, all these things will eventually make sure that we want there's nothing like regulation that prompts adoption of security technologies. So eventually that'll happen. There's been an executive order from the White House that talks about safe, secure, trustworthy AI. And that's how it starts. And eventually you will have regulations, you'll have people worried about biases in the data, discrimination using models. So these are soon becoming bigger models as we adopt AI more and more. So I'm sure, even though in the first use cases, they'll focus on performance. Eventually, I think enterprise is where they'll care more about the security of AI than using ChatGPT or things like that.
Thank you.
Yeah.
Sridhar, I'll ask you a question,
yeah,
if
sure.
I may. So many years back, my team made a trip to Boise to visit Micron, and we were brainstorming different ideas of things that you can add to a DRAM chip. One of the take-homes I got from that discussion is, if the area overhead of adding something is more than 1%, it's likely not an idea that is on the table. And so I'm just wondering if there are similar guidelines, within Intel, right?
Yeah.
So, how large or how low should the overhead be before it can be a candidate for inclusion in hardware?
Yeah. It varies a lot based on use case. When we started SGX, when we deployed SGX in the beginning, the performance overhead was close to 20%. Okay, but because of the use case it was deployed in, people were willing to use it, and eventually over time the performance came down. In your case, because it's memory, the memory market is a lot more cost sensitive. And that's why the 1% overhead. But typically, if you go to a service provider and you say, look, I've got a technology and the overhead is less than 5%, that's a no-brainer. 10% is tolerable, less than 5% is a no-brainer. Yeah.
Michael Jemikin from Seoul National, South Korea. I don't work in that field, but I was curious about there is like some parallel paradigm of multi-party computation and also some hybrid protocols using the HE and MPC. So do you have any thoughts on that, or is Intel also like working on that side?
Are we working on MPC? Is that the question? I'm trying to understand what the question is.
Oh, like I only heard about the HE, so I was curious if that's a part the Intel labs are also working on.
Yes, we're working very closely with Seoul University, actually, on the inventor of CKKS on FHE, and in large part because we won the DARPA proposal, and that's what got us going. In terms of MPC, that's there's a whole class of technology under PETs, privacy enhancing technology, which is getting a lot more popular. The problem with MPC is not that scalable, and so we more focus on FHE than others.
Thank you.
Yes, Joseph Torrellas from Illinois.
Yeah.
You didn't talk about constant time computing. What do you think about it? And given that computers are not deterministic, is there a hope for that?
I think constant time computing is definitely needed for all the side channel attacks. It's very hard, just given the non-determinism in the compute equipment, the time it takes to involve caches and memories and so on and so forth. I think we need that to work. We need that to work in specific algorithms, I think. Like crypto algorithms is a great situation. Rather than come for constant time for a generic algorithm, applying it to some very security-sensitive workloads would definitely be worth it. And cryptography is probably one place where I think I can see value for that. Yeah.
Okay.
Does that make sense?
Yeah.
With that, we'll end the session. Let's thank the speaker.
Okay. Thank you.
And before everybody leaves, just a couple of quick announcements. So when you show up for the excursion this evening, you will not be allowed on the bus unless you show your ticket, which is at the back of your badge. And the second announcement is now we are, in the next 5 minutes, we will start session 6A, B, and C. So there are 3 parallel tracks. 6A is going to be here, and 6B and C are at the end of this hallway. So Atlantico, the 2 rooms on the right and the left. All right? Thanks, everyone.